Where were we? Just did this example, finding the intervals of increasing and decreasing. We can learn even more. That's a lot right there. We can, right? We're just getting started. Okay, the first derivative test. And this really brings things all the way to finding local maxes and mins. We started that back in 4.1 with critical numbers. Now we can find the local maxes and mins. Okay, so the first derivative test, what we're testing for are where local maxes and mins occur. So it's 3 steps, right? We get a lot of these procedures are like broken down into steps, and here's another one. So the first derivative test, step number 1, is to find the intervals of increasing and decreasing, right? That alone is an entire test. But okay, so do that. Then step number 2 is to identify, really once you know where you're increasing and decreasing, you pretty much have it. From that, you can identify, there's really not a lot of work to do at that point. We can identify pretty quickly where we have local maxes and mins. So identify each critical as the x coordinate of a local max, a local min, or neither. Once we have those identified and we're just kind of looking back at that, our domain line and our plus and minus, our pluses and minuses on that line, we can identify those. And then number 3, we're going to find the y values of our local maxes and mins. So we know the x coordinates, then we'll find the y coordinates, and that will be the full point, which will give us the local max or min. So let's do that for the example we were just working with, 2x cubed plus 3x squared minus 12x. Let me switch back over here. Okay, so here it was. So from this example, let's say we got all the way to this point where we knew the increasing and decreasing. Okay, let's say though we didn't want to find out necessarily where we were increasing and decreasing. We wanted to know where there are local maxes and mins. So based off of this chart, we pretty much have it. So we can see, hey, check it out. At -2, what's happening? Would -2 be the x coordinate of a local max or of a local min, right? And we say, well, if it was increasing and then it hit -2, and then it started decreasing, well, that must have been a local max. Whoops, that must have been a maximum. And at 1, right, if it was decreasing and then it hit 1 and then it started increasing, well, that must have been a local min. So right away, we can say, this is a local max. This is a local min. And we can just see it there in our chart. The only thing left to do then is say, all right, let's plug those numbers back into the original function to get their y values. And then we'll have it. Well, if we put -2 back into the original, I went ahead and did that. I got 20 when I plugged that in. And when I plugged in 1, well, that's a little bit easier. 2 plus 3 minus 12, 5 minus 12, -7. So we could see, hey, there's a local max, right, at the -2, at -2, 20. And there's a local min at 1, -7. So it's really the same amount of work as finding the increasing and decreasing. You just kind of take a slightly different direction, or obviously you could easily do both. Okay, let's do another example. This time, well, a new one, a little bit harder. Use the first derivative test to find all local maxes and mins for this x times x minus 4 to the third. Okay. Example. Use first derivative test to find all local maxes and mins. And it's f of x equals x times x minus 4 to the third. Okay, first thing, right? We're creating that chart. We need the critical numbers, which means we need a derivative. How are we going to go about this derivative? Let's use the product rule. Turns out using the product rule here will be much faster to get those criticals than it would be, say, to multiply it all out. Okay, using the product rule, we'll see why that is. Comes down to the factoring when we set it equal to 0. Okay, product rule says 1, and then we'll multiply by our x minus 4 cubed plus x times 3 x minus 4 squared times 1. Okay, looks good. So f prime x equals x minus 4 to the third plus 3x x minus 4 squared. Where does this derivative equal 0? Right, it looks kind of intimidating, but just kind of pause and say, hey, since we're setting it equal to 0, the idea is to factor. Do these have something in common? Yeah, they have x minus 4 squared in common, leaving x minus 4 plus 3x. And wow, we're going to be able to solve this super fast. Okay, quick note. If we had multiplied this all out, you know, that would take a little bit of work, right? A cube and then distribute the x. It wouldn't be that big of a deal, you know, but you'd have to be careful, obviously. The derivative would be quite simple because it's just a big polynomial. But you might run into trouble when you set it equal to 0 and then you have to factor that large polynomial with cubes. You know, getting an x minus 4 squared factor, and what's the other one? 4x minus 4, which actually that we could even factor again, take the 4 out, make it x minus 1, right? Getting, oh, that's the square. Getting factoring like this, you know, from a long cubic, it's not immediate, right? You may even have to like guess and check with synthetic division or something. It's definitely doable, but man, if you just do this with a product rule and then factor out that x minus 4 squared, so much faster. Okay, solving this, we've got two solutions, x minus 4 and x equals 4 and x equals 1. Nice. All right. How about where f prime of x is d and e? Well, again, this derivative, we're never going to be dividing by 0, which is really what we're looking for. So that's a none. Doesn't happen here. Okay, so we got our two criticals. So far, so good. We're going to mark these on the domain lines. We want to kind of pause. You don't necessarily have to write this, but you know, you're just thinking about it. What's the domain of our function? In this case, it's essentially a polynomial. It's just factored in its factored form. It's negative infinity to infinity. Most of the time, that's going to be the case. Sometimes it won't be, so be on your toes. Okay, we're going to look Okay, we're going to establish that domain. We're going to mark our two numbers. Just make sure they're done in order. The 1 first, then the 4. And again, we have these 3 sections. Okay, let's check it out. So maybe here we could use 0, that'd be good. Maybe 2 and maybe 5. So I'm not going to really write those, but I'll know 0, 2, and 5. Okay, I'm going to put those into f prime of x. Let me write that out again. Here was f prime. So you could even factor there. I'm just going to leave it like this. All right, so we got f prime 0. Putting 0 in, 0, so it'd be negative 4 cubed plus, oh, there's a 0 there, so that wipes out everything. Negative 4 cubed is negative 64. Yeah, and it's not important that it's negative 64, it's just the fact that it's negative. So minus sign and like a down arrow. Okay, how about 2, f prime 2? If you put that in, I'll let you check my work. I got positive 16. So plus, up arrow, right? And finally 5. Now you might be thinking, like a lot of people do, hey, you know, once you have one of them, don't they always just alternate positive, negative? No, they don't. No, they don't always do that. Check out f prime 5, right? Now this one's is not so bad. 5 minus 4 is 1, so we got 1 cubed. Same thing here, it's just going to be 1. So we have 1 plus 3 times 5. That's going to be 16 again. That's also positive. Check that out. Okay, negative, positive, positive in our intervals. Now here, we're not worried about increasing and decreasing, although we just found it. We're worried about local maxes and mins. So let's look now at our chart. Notice the only place it switched was at 1. It's going down, then it's going up. This is a local min. What about 4? 4 is neither. It was going up, then the derivative became 0, but then it kept going back up after that. So it didn't, right? It never made a max. It went up, leveled off just at that one point, and then kept going up again. So neither max or min. So we're only going to worry about what's happening at 1. We know that's a local min. Okay, so I'm going to take the 1. I still need the y value. I'm going to put it back into the original here. And what do we have? 1 times, okay, 1 minus 4, negative 3 to the third is negative 27. So we've got a local. We've got a local min at 1, negative 27 right there. We could even say, you know, if we really wanted to, there is no local max. You know, you don't really need to say that, but we just want to indicate what we did find. You know, okay, there you go. Very nice. Let's stop this video here. There is more to come.